Now we're moving on to section 15.2, which is on the equilibrium constant in more detail. So the Haber process, which we'll learn quite a bit about in this chapter, is a way that ammonia was produced, where we take one atom or molecule of nitrogen and 3 molecules of hydrogen to produce 2 molecules of ammonia. So the equilibrium constant depends on, well, ends up being this. It ends up being my products, which are NH3 ammonia squared, divided by my reactants, which are N2 and hydrogen, H2 to the third. Notice that the constant depends on the stoichiometry. So I take all of the coefficients and I raise them to the power. So we'll see how that works in the next slide. So what do you need to start with to reach equilibrium? Do you have to start with nitrogen? Do you have to start with ammonia? What do you have to start with? And ultimately, it doesn't matter. You can start with either the reactants or the products. Now, you do have to have, if there are multiple reactants, then you need all of them, to at least some of all of them. So that way you can get equilibrium, or else you won't have a reaction happen, right? You won't have your molecules collide if you don't have all of the molecules. But you can start with either reactants or products. So let's say here in this first one, I'm starting only with reactants. I'm starting with nitrogen and hydrogen. Now, in the kinetics part, we see that hydrogen's leaving about 3 times as fast as nitrogen, and that has to do with the stoichiometry, right, of our rate of change. But once we have equilibrium, you can see that we have produced our ammonia. And if we took the ratio of our ammonia versus our hydrogen and nitrogen, that would give us the same value for our equilibrium constant, Kc. If we start with products, if we start just with ammonia and no reactants, then our ammonia will react and decompose into nitrogen and hydrogen. And again, the ratio will be the same to give us the same Kc value. So the amount of change is just based on the stoichiometry. So in general, to get our equilibrium constant, if we have our general reaction, which we're very familiar with, A of A plus B of B, we're going to skip C, goes to D of D plus E of E, then our equilibrium constant, Kc, now this will be for concentration values, that's why we give it a C, it's going to be our products divided by reactants. So you're going to get really familiar hearing products over reactants. So our products are D, and then we're going to raise it to the coefficient power times E to the E. Now before, when we had our kinetics, those coefficients or the order, the powers were found experimentally. In this case, it is always related to the coefficients of our reaction. And then we have divided by our reactants, which are A raised to the A power and B raised to the B power. Now, in the case that we have molecules that are all gases, we're going to have some kind of pressure that is exerted. Now, pressure and concentration are related. If I have a higher concentration, then I'm going to have a higher pressure. So when I have a closed system of gases, my equilibrium constant can be found for the pressure, which is Kp, so the pressures. And that's going to be the pressure of the product, so D raised to the D power, times the pressure of E raised to the E power, divided by the pressure of A to the A power, and the pressure of B to the B power. In order to find the conversion between these two, so in general, these are the two equations you will use. On the very, I don't want to say unusual, but every so often you will be asked to convert between Kc and Kp. Not super frequently, but frequently enough that you need to learn it. You will want to convert between the two. And so what you will do is, we know that pressure is related, PV equals nRT. And so if I know that pressure equals nRT over V, I'm going to write it like that, we know that N over V is concentration, right? So what we can do is we get that pressure right here equals the concentration times RT. So what we end up knowing is that we can find Kp, K sub P, is equal to Kc, the constant, times RT times the change in molecules of gas. So basically, if I have A, which is a gas, going to 2B, which is also a gas, then my delta N would be products, which is 2 minus 1. So delta N would be 1. So I will find my moles of products that are in the gas phase minus the moles of reactants in the gas phase for this delta N, because the equilibrium constant with respect to pressure will only be related to the moles of gas. So how much did that change? So once again, this will be used very infrequently to convert between Kp and Kc, but for the most part, you will use these two up here. If you're given pressure, you'll do that. If you're given concentrations in moles per liter, you'll use Kc. So let's practice. I want to find the Kc for these reactions. So I'm going to say for A, and I have ozone turning into oxygen, so Kc is going to be products over reactants. So I have O2 to the third divided by O3 to the second. O2 is my product, and we'll raise it to the third because of the 3. Ozone O3 is the reactant, and we'll raise it to the 2. Products over reactants. B, I will have to find Kc. It's going to be my products, which is nitrosyl chloride to the second due to that, divided by reactants, which I'm going to have concentration of NO squared times by chlorine Cl2. Perfect. And then C, I have silver plus 2 ammonias going to this silver ammonia complex. So Kc is going to be concentration of my products, which is the silver ammonia complex, divided by my reactants, and that would be silver, concentration of silver times the concentration of ammonia squared. Perfect. Okay, in this problem we have the Haber process, which again, nitrogen and plus 3 hydrogens going to 2 ammonia. So Kc is 9.6 times 10 to the, at 300. Kp is, so we want to find Kp at that temperature. So remember that Kp equals Kc times RT to the delta N. So we know Kc, 9.60 times RT. Now notice there are no units for K, so that's a key point, that the equilibrium constant is unitless for both our concentration and pressure equilibrium constants. And then we'll talk a little bit more about the meaning on the next slide of large versus small K values. So calculating Kp now R, we're going to use the gas R because we're dealing with gases. So 0.821, and then we will multiply that by our temperature. Now this is going to need to be in Kelvin. So we're going to do 300 plus 273, which is 573 Kelvin. And raised to the delta N. So delta N is going to be moles of gas products minus reactants. So let's see, I have 2 moles of gas product, and then my reactants, both nitrogen and hydrogen are gases. I have 1 plus 3, so I have 2 minus 4 reactants. So delta N is -2. So I'm going to raise that to the -2. So if I put this in my calculator, I'm going to type in 9.6 times parentheses 0.0821 times 273 and 573 and parentheses raised to the -2 power, and what I get is 4.34 times 10 to the -3 is my Kp. Great. Okay, for this last one, we have an equilibrium of sulfur trioxide going to sulfur dioxide and oxygen. Kc is 4.08 times 10 to the -3 at 1,000 Kelvin. So finding Kp, once again, Kp equals Kc times RT to the delta N. So we'll plug in our Kc, 4.08 times 10 to the -3 times RT. R is 0.821 times 1,000 Kelvin. Now delta N. So I have 1, 2, 3 products in gas form and 2 reactants. So 3 minus 2 is to the first power. So when I plug that in, my Kp ends up being 0.335. So the last thing we're going to work on here is just demonstrating how equilibrium constant gets determined. So I could start with, for that one example where we have N2O4 going to 2 N2Os, or NO2s, I could start out with only my product here, and then I will find, and no reactant. Okay, so in this case, it's almost like this. 2 NO2s going to N2O4, right? So the reverse reaction is happening. And I will get a certain amount of my product, and then my equilibrium amount of my reactant will be different for each one. But either way, if I take the ratio of these two together, I get this value, the same value, pretty much within error. If I start out with reactant and let that go to equilibrium, then I take my ratios, and once again, I get my same Kc value. So the ratio of NO2 to N2O4 remains the same, or remains constant. So it doesn't matter how much you start with, the ratios of your species involved in your chemical reaction will always give you the same ending value or ratio of values.